This is VLSI data conversion circuits, lecture 60. In the last class we were looking at a prototype DAC where the noise due to mismatch is shaped outside the signal band, and you can leave it when you can the basic idea is to divide and conquer. So you take for instance a 3-bit DAC with 5 levels and split it into 2 sequences which occupy 1 bit less, so there are fewer levels, right, and one of them is related to the other through this sequence S. So the output at this layer is nothing but V by 2 plus S by 2 and V by 2 minus S by 2. Since this happens 2 layers away from the last layer, I call this S2. Now since we have 2-bit sequences, each of these can be split into 2 1-bit sequences, and finally what you have is V2 V by 2 by 2, which is V by 4 plus S2 by 4 plus S1A, I will call this S1A, S1A by 2 and V by 4 plus S2 by 4 minus S1A by 2, correct. This is the same, right, and the only difference is S1A by 2, and similarly here you will get V by 4 plus S1 V by 4 plus minus minus S2 by 4 plus minus S1B by 2. So basically the thermometer drive waveforms will be V by 4 plus minus S2 by 4 plus minus S1 by 2, where plus happens to be S1A and okay, and S1B respectively. So clearly we see that each thermometer drive waveform is linearly related to the input, right, and has got in addition these sequences. These sequences have a spectrum which we have designed to be shaped, right. So if there was no mismatch in these unit elements which these thermometer drive sequences will be driving, what can you expect to the combined waveform? It will be exactly the same spectrum as V, because at every layer of hierarchy we have ensured that the sum of the split sequences is exactly the same as the input, which means the sum of all the thermometer drive waveforms, right, or the drive sequences at any instant of time will be exactly the same as V at that instant of time. Does it make sense? All right. Now if there is mismatch, what do you expect to happen? There will be some residuals of S1 and S2 coming out, and the shape of these sequences, the spectral shape of these sequences will appear in the final output spectrum, correct. In the if we assume first order noise shaping, then for S1 and S2, then when there is DAC element mismatch, you will find that the mismatch noise, right, which was white when we randomized, should now have a first order noise shape. alright, and this should be a huge improvement over or pure randomization. Does it make sense? So, let us before I show you the simulation results, this is the spectrum of V alright, and I have deliberately offset these two sequences V1 and V2, one is in orange and one is in green, okay, and the sum of these, I mean this is actually the 0 for these two sequences, okay, I have just offset them for visibility on the graph. The sum of these two sequences V1 plus V2 is V, and how many levels are there in V? This is a 5 level sequence. How many levels are there in V1 and V2? 3 level sequences, correct. So, how many bits are required to represent this? 3 bits. What about this? 2 bits, right. And now you can go and decompose V1 and V2 into 2 single bit sequences, and these are the PSDs of T1, T2 and T3 and T4, which are the PSDs of the individual drive waveforms of the unit elements, and as usual we can see that the signal component in each one of them is the same, correct, and you can see this shaped sequence, and this corresponds to that S2 by 4 plus S1 by 2, right, or vice versa, whatever. The important thing is to note that this has got a noise shaped spectrum, first order noise shaped spectrum. This is the spectrum when there is no mismatch, and that corresponds to the same NTF and stuff that we have been using for all our simulations, correct, okay. And clearly when there is mismatch, the cancellation of these shaped noise sequences, that shaped noise part is not exact, so you are left with a residual, right. For 1% random mismatch, you see that you are a little above the ideal SNR that, or ideal SQNR that you would have got, you understand, all right. So, now let us see this on a log scale, and with 1% mismatch, the noise due to mismatch is so close to the quantization noise that, I mean, you are not able to see the first order noise shaping of the mismatch noise itself, okay, all right. So, if you plot this on a log scale with more mismatch, so that the mismatch noise dominates, this is 5% mismatch, and this is a log scale, as is evident from the graph, okay. These are the spectra of the individual thermometer drive waveforms, and as you can see on a log scale they must go as 20 dB per decade, right, which is definitely happening. And when there is mismatch, you see that the residual is also going at 20 dB per decade, and this makes sense, right, okay. And the ideal one is this part, and the spectra of the mismatch shaped DAC and the ideal DAC coincide at at high frequency, okay, only at low frequency is where they were supposed to cancel out, right, and there is small residue. Now, what is one obvious comparison that we would like to do now? Okay, we have seen two techniques where distortion is removed, right. One is pure randomization and other one is this noise shaping, right. One obvious thing is to say see how we are doing in this case compared to the other one, okay. With 5% random mismatch, you can see that this is the ideal, all right. This is with randomization, all right, and this is with first order mismatch noise shaping. Right, and you can see that you have gained significantly, right. If you assume that this is the band edge and most of it is getting contributed here, you can see you have gained a good 40-50 dB, right. And this 5% mismatch happens to be a really bad example as far as mismatch is concerned. I mean, just because you have something which shapes the mismatch noise out does not mean that you can go and deliberately go and build a lousy DAC, right. So, it turns out that I mean, if you do within quotes use standard best practices for layout, right, it is not uncommon to get matching in the order of 0.5% or so, right. Sometimes capacitors can match to, if you do a good job, can even match to like 0.1 to 0.05%, right, which is at the matching at the 10 to 11 bit level. So, even if this is 5% mismatch and you are this much above the quantization noise floor, if the mismatch became 0.5% rather than 5%, what do you think will happen? Pardon? What will happen? I thought we discussed this the last time around. It will go down by half, right? Power is go down by 10 dB, right? Sorry, by 20 dB, right? Because square and then power, right? So, so that basically means that if you have 0.5% distortion, you probably won't be able to see. I mean, with mismatch, with first order mismatch noise shaping, the spectrum you would see would be pretty much the same as the ideal spectrum. Does this make sense? Okay. So, one thing that one could ask is, hey, what is so special about first order noise shaping? Why not shape it with higher orders? I mean, that is definitely possible, except that this thing becomes a little more complicated, right? And so on. And actually, most of the time, right, the mismatch is, as I said, is small enough, right? Let us say 0.5% is conservatively speaking, an alright number to choose for mismatch in the unit elements, in which case at these levels like 100 plus dB levels, you still do not see any degradation due to once your first order noise shape, because once your first order mismatch noise shape, you are almost at the theoretical SQNR level. So, then you might say, what is the point in trying to make a second order noise shaped version where yeah, it is true that the mismatch noise will be even smaller, but you are dominated by quantization noise anyway, so why bother, right. So a lot of times people just end up stopping with first order mismatch noise shape, you understand. So this is I mean, so this line of investigation, right, has been, you know, is responsible for this tree shaped or tree structured mismatch noise shaped attacks, all right. And you can see that there is a logical progression between what we wanted to do and what we eventually did, correct. Historically, of course, you know, people thought completely differently, and so you found that, you know, I mean, that line of thought gives rise to a whole bunch of mismatch noise shaped architectures, where the benefits due to mismatch noise shaping are not as evident as they are here, right. Here we knew what we were doing, we implemented exactly that, and the fact that we should expect mismatch noise shaping, the fact that we should expect first order residual noise is all very apparent, right. But the original thought process behind mismatch noise shaping are somewhat different. I will again illustrate this with our 4 level example. Okay. So, there are 3 unit elements. So, I mean, when the levels of the DAG, please note that again, as I said, this line of thought is somewhat more ad hoc than the clean set of reasoning that leads to the tree structured mismatch shaped DAG, all right. Many of these techniques also happen to be first order, will give you a mismatch noise which is shaped to first order, right, but that is not evident from the discussion, or unless you know, you think about very carefully, it is not very obvious that the mismatch noise shape, I mean, the shaped noise is actually first order, all right. And many of these have are, if you kind of do a search with you know, dynamic element matching, you know, in the literature for the last 20 years, you will find you know, a bazillion schemes, right. And several of these techniques, which are, you know, kind of based on the intuition that I will describe, are what you call are not as nice and rigorous as the tree shaped structure, and but I will explain the basic intuition as I go along, right. So, if you consider a 4 level DAC with 3 unit elements, you have, when the code is either 0 or 3, there is only one way of choosing the elements. When the code is 0, all elements are off. When the code is 3, all the 3 are on. So, whether it is 0 or 3, there is no freedom of choice. Okay. If the errors in each one of these elements are delta 1, delta 2 and delta 3, then you the full scale is 3 plus delta 1 plus delta 2 plus delta 3, the lowest point is 0. However, in the middle, for example, if the input code is 1, then there are 3 ways of choosing one element, right, and each one of these ways results in a different error. Okay. Now, there are 3 ways of choosing 2 elements also, and these are shown here. So, each of these circles represents one way of choosing element such that you get a nominal value of 2. Okay. Now, the interesting thing is that if you look at the center of gravity of each of these levels, what is the center of gravity of this? There is only one level. So, okay, so that will be 3 times 1 plus delta 1 plus delta 2 plus delta 3 by 3. So, this is I am just written this as 3 times 1 plus sigma delta I divided by 3. Now, what is the center of gravity of these 3 levels? Is nothing but take all these 3, add them up together and divide by 3, and that will be 2 plus sigma or 2 sigma delta I divided by 3, which can be written as twice 1 plus sigma times delta I by 3, is not it? So, and similarly for this it will be 1 plus sigma delta I by 3. So, and the center of gravity for 0 is 0. So, if I draw a straight line as shown here, are you able to see the dull grey line? If that has a slope of 1 plus sigma delta I by 3, right, the centers of gravity of each of these codes lies on a straight line. Okay. I have shown this for a 4 level DAC, but it is true for an arbitrary number of levels. If you have an n level DAC, then there are n minus 1 unit elements, and the number of ways of choosing a code k is n minus 1 choose k. There will be so many, so in general for a large number of levels, you will basically find that there will, you can draw a hypothetical straight line, and for each code there will be a whole number of ways of doing this, right, but the center of gravity of all these will lie on a straight line. Okay. So, based on this observation, right, a whole bunch of schemes came up. So, to give you some intuition, if okay. So, ideally, if you use the thermometer type decoder, your DAC would have the same element every time. So, the characteristic of the DAC would probably be some nonlinear thing like that, correct. So, then the obvious thing is to say, on the average I want a straight line. So, sometimes I will choose this, sometimes I will change my choices of unit elements and do this, right, keep changing this often enough, and therefore, on the average I must get the straight line. Okay. So, this has spawned a whole bunch of techniques. The first one based on the on this observation, let me also point out another way of saying the same thing. The centers of gravity of all these codes is this red dot shown here, correct. So, if I look at the deviations of from this red dot, the sum of all the deviations must be by definition that is the center of gravity, is not it, right. So, the sum of all the deviations of a particular code from that hypothetical straight line, right, which passes through the centers of gravity of all these code choices, right, is 0, and that is true for any code. Okay. So, based on that intuition, the first technique, one of the first techniques that came up was what was called individual level averaging, and the idea is the following. Conventionally, if you have V equal to 1, only the lowest element in the thermometer decoder will be 1 or will be driven to 1. So, you will be using this always. Now, with individual level averaging, what you say is that, okay, the first time I get a 1, I will choose the first one, the next time I get it, I will choose the second one, the third time I get it, I will choose the third unit element, and the fourth time I will come back to the first and keep repeating, right. So, you can see that in 3 clock cycles, okay, the error, so the absolute error is this, but the deviation from the hypothetical straight line goes to 0 once you go through all these things, okay, and so on, right. And though it is not apparent until it is pointed out, you can see that the thermometer drive waveform will have a mean which is V by n level minus 1, and in general if you have a slowly varying V of t, V of n, you can expect the mean value of each of these thermometer drive waveforms to also be V by n level minus 1. Okay. It is not very apparent that mismatch is noise shaped, right. Since, I mean, one thing you can say is that if you think of the error sequence, the error goes to 0 after, or sorry, the accumulated error, right. So, sigma error goes to 0 after every 3 cycles in this example, right. Now, if the accumulated error goes to 0 after 3 cycles, in general you can say that regardless of the, if you go on, if you look at the accumulated error after a lot of time, right, this accumulated error is always bounded, yes, because after every 3 cycles is going to 0, right. So, wherever you stop, this accumulated error is bounded. Does this make sense? Okay. Or this accumulated error is finite. Okay. So, if the accumulated error is finite, then what can you say about its low frequency content? If the accumulated error is bounded, in other words, if you have a waveform, you integrate it and its output voltage is constant, the output of the integrator is constant, what can you say for the content at low frequency? DC value must be 0, correct? Does it make sense? Otherwise, I mean, if there was a non-zero DC content, you integrate it, it will blow up, right. So, if you have a sequence and if you accumulate it, if it still remains bounded, correct, which means in the worst case you can only have a DC content after accumulation, it must follow that it has a notch at DC, right. If it is 0 at DC, then it follows that at low frequency it is probably small. Does it make sense? Okay. So, that is the intuition for first order noise shape, right. So, the accumulated error is bounded, which means 0 at DC, all right. So, when the input is varying, what is done is the following. So, I hope you are able to see two colors for the pointers. Okay. Please now just focus your attention on the ones in the input, all right. So, when the input is 1, okay, we start off with the, we have a pointer which starts off at the lowest element, and this pointer is colored here in violet. The next time I get a 1, right, this pointer, you start from the pointer, and the pointer is simply the accumulated version of where the pointer was earlier plus 1, okay. The third time, and then the pointer must then move to all right, and then the next time you get a 1, the pointer must move modulo 3, okay, and then the pointer moves right. So, for each input level you have a pointer, right, and that pointer keeps, you keep starting from where you left off for that particular or for that individual level, right. And I mean, in other words, it is like this, there is no difference between. So, if you just look at those instants of time where v equal to 1, if I picked out only those pictures and put them side by side, this is how it will look, correct. And as we already saw, the accumulated error here is bounded, which means that it has a 0 at DC, all right. Now, if the same thing is done for all other individual levels, then the same thing will happen to the errors contributed by those sequences also. So, for example, for the input level of 2, you start off with 0, the next time around the pointer moves to 2, then the next time you get 2, which is here, 2 plus 2 is 4, 4 modulo 3 is 1. So, the pointer moves there. The next time you get a 2, you start here, actually this is a mistake, you must start here, and the next time around the pointer will be, the pointer for 2 will start there. Does it make sense? And just like, and look at the error here, it is delta 1 plus delta 2, the error here will be delta 1 plus delta 3, and the error here will be delta 2 plus delta 3. So, when you add these 3 sequences, it will become 0. I mean, whenever you hit delta 1 plus delta 2 plus delta 3 times 2, right, you are done, correct. So, if you take a sequence which is just for these 2's, that must also have a notch at DC, correct. For 0 and 3 there is no need to have pointers because there is only one way of choosing them, correct. So, if you look at the accumulated error sequence, since each one of these sequences, each one of these accumulated error sequences is bounded, it follows that if you find the accumulated error sequence for this when the input is varying, that will also be bounded, yes, okay, which means that at low frequency you will have at DC you will have a notch, at low frequency it will go as 1 minus Z inverse, okay. So, this I mean this still does not mean that there is no harmonic distortion, right, because it is not clear at least from the discussion we had that these thermometer drive waveforms are linear functions of the input. I mean it is true that the mean of the thermometer drive waveform is the same as the input, but I mean that does not mean anything, right. You could also have some distortion components, and that could then show up as tones in the output. Now, a very popular algorithm which is a variant of which is slightly different is what is called data weighted averaging, okay, and the idea is this. So, the pointers for the individual levels are done away with, okay. So, let us assume that this is the sequence, the pointer starts at 0 or at the lowest level, then the input sequence is 1, the pointer moves here, the input sequence is 2, and so you start the thermometer from here and go there, and the pointer comes back to the lowest level because it is modulo 3, right. If you start from 1, actually it should be modulo 2, 0 1 2 and then it comes back. So, then it is 1, it goes here, then the input is 0, so you stay there, okay. Then it becomes 2, so the pointer moves to 0 again, and so on and so on. And again, as you can see, what happens, the accumulated error is delta 1, right, plus delta 2 plus delta 3 plus delta 1, right, and plus 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 and so on, okay, all right. And please know that you want to look at the deviation of this from, you must assume that what you are interested in is not deviation from the ideal line with the slope of 1, but from the line with the slope of 1 plus delta 1 plus delta 2 plus delta 3 by 3, right. So, you should subtract so basically you are looking for deviations from the center of gravity, okay, all right. So, once you do that, you will find that this accumulated error is also bounded, which means that this also must lead to first order shaping of the noise. Does it make sense? Okay. So, and this is a very popular algorithm used in many practical delta sigma modulators. One of the selling points of this technique is that the implementation is actually quite straightforward. So, what you need to do is you need to have a pointer and you need to keep accumulating and moduloing the result, okay, and so you can just keep starting the thermometer the next time from where the pointer stops, okay. So, you have a pointer, your thermometer code starts from there and you keep counting V number of elements, and if you overflow you start again from the bottom, right. One thing you must understand is that again for every code the number of unit elements which are on is exactly equal to V, right. If V of n is the code, the number of unit elements on is V of n, regardless of what DAX, all the DAX we have seen, whether it is randomization, whether it is tree based EM, whether it is individual level averaging, or whether it is data weighted averaging, all right. So in the absence of mismatch, all of them will perform the same way, right. So this is a, let me just add, this is a very popular technique, right. Again, if you look at each of these thermometer drive waveforms, they will contribute equally to the total output, okay. Does it make sense? Yes, no, all right. And it turns out that you can show rigorously that if you want a unit element type DAC to be insensitive to or less sensitive to mismatch, then each one of these drive waveforms must be a linear function of the input plus some shape noise type component, okay. So I mean, so far we have said that if that is true, then it will be insensitive to mismatch, right, but you can also show rigorously that the opposite is true, which is if a DAC is insensitive to mismatch, then each one of these thermometer drive waveforms will be linear functions of the input plus shape noise, right. So regardless of whatever you do to come up with the final DAC, right, if it is indeed doing mismatch noise shaping without adding distortion and so on, it will turn out that each one of these thermometer drive waveforms is what do you call a linear function of input plus some shape noise, okay. With DWI you can actually work through this pointer business and show that that is indeed the case, right. It is a very kind of a messy thing, but that is what it is. So a lot of these things were not apparent when DWI came out for the first time, right. I mean, so the realization that that each thermometer drive waveform must be a linear function of the input plus shape noise, I think took about at least maybe about 6 or 7 years after all these dynamic element matching techniques started coming out. So you can see that the way it has been presented in this class is not the chronological way in which things happened, right. So you will find unfortunately that a lot of the literature is pretty much okay, a new technique to do dynamic element matching, and you look at it and it is not immediately clear why it is why it works or why it is any better than prior art, okay. Chronologically, the first technique that was proposed was randomization, right, where people saw that distortion goes away but the noise floor rises, and then these mismatch shaped techniques started coming out, and as I said, the first family of techniques were all based on this observation that there are many ways of choosing elements to get the same output, right. To get a output of 1, you can choose in our particular example unit elements in 3 ways and so on, right. And they observed that the average of all these the centers of gravity will all lie on a straight line. So a lot of the techniques kind of exploited that observation, right. It is only I think in the mid 90s, around 93 or 94, that people realized that you must you can realize this mismatch insensitive type performance or mismatch shape performance by making each one of these drive waveforms a linear function of the input plus some shape noise, and that naturally lends to the tree type structure, right. There are other equivalent ways of looking at the problem, right, and you can find that in Schreier's textbook, all right, but this is what I had to say. So, finally, to just look at the drive waveforms of the individual elements in the DWA algorithm, you see that this is the ideal spectrum, all right, and these are the spectra of the individual drive waveforms, and it is indeed first order noise shaped, okay. And if you compare, this is one of them spectra of DWA and the other one is first order tree structured data weighted, I mean mismatch shaped mismatch shaping of noise, sorry, noise shaping of mismatch, all right. You will see that they kind of have the same first order slope. They are slightly different here simply because the absolute numbers chosen for the mismatch were different in the two simulations. So, there is some I mean these two are not bang on lying on each other, right. So, the bottom line therefore is that in a sigma delta modulator, if you want to realize it as a multi-bit structure, you want to have a loop filter which is either continuous or discrete time. You have a multi-bit flash ADC, right, and before you go into the DAC, you have to get into this block logic which takes the code from the ADC, figures out what to do in order to make these thermometer drive waveforms linear functions of V plus some shape noise, okay. So, this element this is called dynamic element matching, in the sense that the matching is not intrinsic, right. You are getting matching dynamically by doing stuff to the thermometer drive bits. So, this is often abbreviated as DEN. Okay. Now, this is combinational logic which therefore has the penalty of, pardon. So, this I mean logic will add delay, correct. So, there will be I mean so DM will cause excess loop delay, right. That might be small when you are operating at low sampling rates, but can become a problem if you are trying to realize very high speeds and the delay of this may become a significant fraction of the clock cycle. Does it make sense? All right, thank you.